Right now, as you listen to this, your brain might be quietly erasing its own memories. And I don't mean that in some poetic passing of time kind of way. I mean an active physical demolition where your own immune cells are literally tricked into eating the microscopic connections that hold your identity together. So welcome back, learner. Today, we are exploring the absolute boundaries of human cognitive autonomy.
Yeah, that invisible line between who you are and, the biological machine that houses you, it is the ultimate existential tightrope, honestly.
Mm.
Because autonomy is fundamentally about preserving your inner self.
Mm-hmm.
But what happens when the physical body becomes a cage?
Right.
Or conversely, what happens when the physical body is totally fine, but the mind itself just begins to unravel from the inside out?
Which is terrifying. And that is exactly the mission of this deep dive. We are looking at this massive convergence of recent scientific literature. Rather than just skimming through some papers, we are going to look at the raw biological mechanisms of how we actually maintain control of our minds. We are going to explore how we are literally hardwiring technology into the brain to restore a lost self, how the brain violently cleans its own tissue while you are unconscious, and, the exact daily habits that can physically build an impenetrable fortress against cognitive decline.
And the connective tissue between all of this, the thing you have to keep in mind, is resilience. The human brain is not a static organ. I mean, it is aggressively dynamic.
Yeah.
And the latest research from 2024 to 2026 shows that whether we are talking about a patient with total paralysis or just someone trying to avoid dementia in their 80s, we are finally figuring out how to manipulate that dynamic system.
So let's start with the extreme end of the spectrum, when the biological body completely fails. Because the leap we have made in brain-computer interfaces, or BCIs, over the last couple of years is just hard to overstate.
It's basically sci-fi made real.
Totally. There is this deeply moving story published out of UC Davis involving a man named Casey Harrell. Casey has ALS, amyotrophic lateral sclerosis. And for anyone unfamiliar with the mechanics of ALS, it is a neurodegenerative disease that strictly targets the motor neurons.
Right.
So your cognitive function, your personality, your memories, they all remain perfectly sharp. But the electrical cables connecting your brain to your muscles just disintegrate.
Which creates a condition known as a locked-in state.
Okay.
To understand the sheer terror of this, learner, imagine waking up tomorrow and realizing you cannot move a single muscle in your body.
Oh, man.
You cannot open your eyes, you cannot swallow, and you certainly cannot speak. But your mind is racing. You are entirely present, but you have literally zero output mechanism to the physical world.
Which is just a nightmare. And for decades, the best assistive technology we had for this was incredibly primitive.
Yeah.
Right.
Very, you might have an eye tracking camera
Yeah.
where the person laboriously stares at a screen, spelling out words letter by agonizing letter. It is exhausting, and it just completely strips away the nuance of human interaction.
But Casey didn't use an eye tracker. He received an intracortical brain-computer interface. Now wait, stop right there. Whenever I hear the word intracortical, I assume we are talking about serious, highly invasive surgery. Like, are we talking about taking a drill to the skull?
Well, we absolutely are.
Yeah.
Intracortical means it goes beneath the cortex.
Yeah.
So this isn't some high-tech swimming cap you just wear on your head.
Right.
A surgeon actually performs a craniotomy. They remove a piece of the skull, and they physically implant a small array, often a silicon chip, covered in hundreds of microscopic needles, directly into the gray matter of the brain, usually right into the motor cortex.
Wow, so they are just stabbing a chip into the brain tissue.
Essentially, yes, because these microelectrodes have to sit right next to the individual neurons just to listen to their electrical chatter.
Okay, so they drill into his brain, plant these microscopic microphones right next to the neurons responsible for speech, and wire that up to a computer. What exactly did Casey manage to do with this setup?
He achieved genuine, unassisted autonomy, which is huge.
Yeah.
He didn't just type out a few words in a lab setting while a dozen engineers hovered over him, monitoring the connection. Nature Medicine reported that he used the BCI to operate digital platforms, communicate with his family accurately, and he even sustained full-time, independent work over a 2-year period.
Wait, full-time work?
Yes. He moved from being a medical demonstration to just, living his life.
Which is incredible. But I want to get into the mechanics of the communication itself, because the biggest problem with older speech prostheses wasn't just the accuracy, right? It was latency.
Lag, yes.
If you've ever watched a news broadcast with a bad satellite connection, where the anchor asks a question and the reporter just stares blankly for 3 seconds before answering, it completely kills the rhythm of the conversation.
It destroys it. That lag destroys the micro-timing that makes human interaction actually feel human. Like the pacing of a joke or that quick interjection to agree with someone, the emotional cadence, all of that relies on sub-second timing.
Yeah, totally.
If it takes you 4 seconds to generate a word on a screen, I mean, you are no longer having a conversation. You are basically sending telegraphs.
So how did the researchers solve the lag? Because it takes massive computing power to translate raw electrical brain noise into a perfectly spelled English word, right?
They solved it by abandoning the idea of spelling words altogether.
Really?
Yeah. Researchers at UC Berkeley and UCSF developed an AI model that doesn't look for letters at all. It looks for phones and motor intent. Because when you speak, you don't think about the letters in a word.
Right. I'm not picturing a C, then an A, then a T.
Exactly. Your
Yeah.
motor cortex sends this incredibly complex, orchestrated sequence of commands to your jaw, your tongue, your lips, your vocal cords, and the AI just intercepts those commands. It recognizes the specific neural pattern for the sound, boo, or
Ah.
and because the AI uses predictive architecture, it actually anticipates the intended sound before the neural command is even fully executed by the brain. So it streams intelligible speech in near real time.
That is wild. It's like playing a well-tuned instrument instead of typing. The thought immediately becomes the action. But what if they can't even attempt to move their mouth? Because I'm looking at the data from Stanford Medicine in 2025, and they talk about detecting inner speech.
Yeah, that is a massive breakthrough.
If the patient isn't trying to physically move their vocal cords, how does the machine know what they are thinking? Is it literally reading an internal monologue?
This is where the neurobiology gets truly wild. When you talk to yourself in your head, your inner monologue, you might feel like it's completely silent and contained in some abstract, thought space.
Yeah, it feels like it's just floating in there.
Right. But neurologically, your brain is still generating a highly specific physical pattern of activity. The language centers in the brain, like Broca's area, are still lighting up. They are still structuring the syntax and the semantics.
Even if you aren't trying to speak out loud.
Exactly. And the Stanford study proved that a highly tuned BCI can actually pick up the neural representation of that internal word formation. It entirely bypasses the motor cortex's attempt to move the mouse. The inner thought directly becomes the digital text.
That feels like literal telepathy. I mean, that is mind-blowing, but surely there's a catch. If you have a silicon chip stabbed into your brain tissue, the biological environment isn't static, right? The brain is squishy, we breathe, our blood pressure changes, our tissue shifts.
You've hit on the exact reason why this technology has been stuck in the lab for 20 years. Calibration fatigue.
Okay, unpack that.
Well, the brain is not a motherboard. It is a hostile biological environment. When you insert a foreign object like a silicon electrode array into the cortex, the brain's immune system immediately recognizes it as an invader. Astrocytes and microglia swarm the area. They try to isolate the threat. They form scar tissue right around the electrodes in a process called gliosis.
It's like getting a microscopic splinter that the body just tries to wall off.
That is exactly what it is. And as that scar tissue builds up, it muffles the electrical signals. On top of that, your neurons naturally change how they fire based on your fatigue level, your stress, your caffeine intake.
So the signal is constantly changing.
Right. So in the past, a patient would wake up, turn on their BCI, and the machine would just output gibberish. The signals had shifted overnight. They would have to spend an hour every single morning staring at a screen, reading specific prompts, just to recalibrate the algorithm.
Yeah.
Exhausting.
But the new systems have something they call plug-and-play stability. So how do they bypass the scar tissue and the shifting signals?
They use large language models,
Mm-hmm.
very similar to the architecture behind modern AI chatbots. It essentially autocorrects the neural drift on the fly.
Very clever.
Yeah, the AI has learned the vast statistical probability of human language. So if the brain signal is slightly degraded because of that scar tissue and the BCI decodes something that looks like "I want a cup of CXFEE," the language model instantly recognizes the context. It corrects it to coffee without needing any manual recalibration.
Right.
And because of this, some patients have maintained stable brain-to-text communication for months without having to retrain the system.
And I see researchers are pushing that even further with what they call neural digital twins, which is a crazy concept.
It really is.
Instead of just relying on an autocorrect algorithm, the BCI runs a continuous, highly personalized simulation of the user's specific brain system in the background. So it actually models how your specific neurons are shifting over time. You just wake up, turn it on, and the digital twin has already adapted to how your brain signals have changed overnight.
Which is absolutely essential when we start talking about bidirectional systems.
Bidirectional meaning two-way.
Right. Because moving a cursor or generating text is a one-way street, brain to computer.
Right.
But true autonomy, especially physical autonomy, requires information to flow back from the computer into the brain.
Okay, right. The exoskeleton studies. I was reading about patients controlling walking robotic exoskeletons with their minds.
Yes, but early exoskeleton trials revealed a massive problem. The patient could think, step forward, and the robotic legs would move. But without any sensory feedback coming back from the mechanical feet, controlling the suit was dangerously clumsy.
Oh, so?
Think about trying to pick up a delicate crystal glass while wearing thick, heavy winter gloves. And your hand is completely numb from the cold.
Oh, you have no idea how hard you are squeezing.
Exactly. You either drop the glass or you crush it.
Because you lack proprioception, the body's innate awareness of where it is in space.
Precisely. Your brain constantly relies on millions of sensory data points from the soles of your feet to make micro-adjustments to your balance. Without that data, the brain is flying blind. So the breakthrough in bidirectional BCIs is that they don't just read motor commands. They also inject electrical current back into the somatosensory cortex.
Wait, the part of the brain that processes touch.
Yes. When the robotic foot hits the floor, sensors on the foot send a signal back up to the brain implant. The implant then stimulates the cortex to simulate the physical sensation of stepping on the ground.
No way. So they can actually feel the floor through the robotic legs.
They can. And that doesn't just restore movement. That restores the fundamental psychological feeling of inhabiting a physical body.
That is just, it closes the loop, it makes them whole again, and the ambition is moving even deeper into the brain, right? There is a 2026 BCI design that targets the lateral ventricles.
Yes.
What are the lateral ventricles? I thought the motor cortex was right on the surface under the skull.
The motor cortex is on the surface. But the lateral ventricles are these deep, fluid-filled cavities right in the center of the brain. They act as a sort of highway system. If you can safely deploy recording devices into these deep spaces, you aren't just listening to motor commands anymore.
What are you listening to?
You are getting incredibly close to the hippocampus, the amygdala, the prefrontal cortex. You are sitting right next to the structures responsible for memory formation, complex emotional regulation, and deep executive decision-making.
Okay, wait. Let's take a step back from the medical miracles for a second here. Because if this technology moves from paralyzed patients to the general public, and, it will, I wouldn't trust tech companies with my browsing history, let alone a wire tapping directly into my memory and emotion centers.
Oh, absolutely.
If I have a device continuously streaming my deep brain activity to a server to help me navigate an augmented reality headset or communicate seamlessly, who is to say it's not picking up my anxieties, my biases, my passwords, or just like random intrusive thoughts I would never say out loud? Isn't this a massive privacy nightmare?
It is, arguably, the single greatest ethical crisis in modern neurotechnology. And it's exactly why UNESCO rushed to adopt global ethical standards on neurotechnology recently. The privacy risk isn't just that someone might intercept the text of an email you're trying to think type.
Right.
The real nightmare lies in the raw neural data itself.
Explain that. What's the difference between the intended text and the raw data?
Well, when a machine learning model listens to your brainwaves to figure out if you want to type the word hello, it has to ingest a massive, chaotic stream of high-resolution electrical activity to find that word.
Okay.
That raw stream contains your intention to type, yes. But it also contains biological markers about your current emotional state, your level of physical fatigue, your baseline anxiety, and potentially even early biomarkers of neurological diseases like Parkinson's or Alzheimer's.
Wow. So it knows everything about your physical and mental state.
It's the equivalent of asking someone to borrow their car to drive to the store. And in the process, they download the entire history of everywhere you've ever driven, how fast you accelerated, what music you listen to, and your exact heart rate while driving.
And in a world driven by data brokers, an advertising algorithm that knows my exact emotional vulnerability at like 3:00 p.m. on a Tuesday is a dystopian goldmine.
Exactly. It's terrifying. But engineers are proposing architectural solutions to this. One of the most promising ones from 2026 is called the SENSE system.
Sense. What does that stand for?
It stands for Efficient EG to Text. through privacy-preserving semantic retrieval.
Okay, I am going to need an ELI 5 explain. Like, I'm 5 on privacy preserving semantic retrieval. What does that actually mean in practice?
It basically means breaking the connection between your brain and the cloud.
Okay.
In a traditional setup, your raw, highly sensitive brain data is beamed up to a massive server farm where a giant AI processes it. The Sense system flips that. It uses a lightweight, highly efficient model that runs locally, entirely on the microchip sitting on your head or your smartphone.
So it never leaves my device.
Right. It acts as a localized firewall.
Yeah.
It extracts only the specific semantic meaning, such as the intent to type hello, and it sends only that single sanitized text command out to the world. The raw neural data, all your emotional and biological background noise, never leaves the physical room. It is processed and immediately deleted on the local device.
A firewall for the mind. I love that. Okay, so we have this incredible technological bridge being built to restore autonomy when the physical body fails. But what if the biological hardware of the brain itself starts to fall apart? Because technology is great for bypassing a broken spinal cord, but if the neurons themselves are dying, the BCI has nothing to listen to.
Exactly. It needs healthy tissue.
So to maintain our autonomy, the brain has to physically survive, and that requires a violent, aggressive maintenance routine. We have to talk about the neurobiology of sleep.
We absolutely do, because the science of what sleep actually accomplishes physically has evolved so far beyond the old assumption that it's just a passive state of resting.
Right, it's not just turning the TV off.
No, sleep is a highly active, metabolically expensive biological reboot.
I want to dive straight into the brain's self-washing mechanism, specifically this massive 2026 discovery regarding lipid clearance. For a long time, we've known about the glymphatic system, right? The idea that cerebrospinal fluid flushes through the brain at night to clear out waste. But this new Nature study shows the brain doesn't actually clean itself alone.
It doesn't. And to understand why, we really have to look at the architecture of the brain. The brain is an incredibly exclusive, highly secure environment. It is protected by the blood-brain barrier.
Right, the bouncer at the club.
Exactly. It's a tight layer of endothelial cells that act like heavily armed border guards. They stop toxins, bacteria, and even the body's own immune cells from entering the brain tissue. The brain strongly prefers to handle its own business.
It's a walled city. It keeps the gates locked during the day so nothing from the bloodstream can contaminate the fragile neurons.
But during the day, the neurons are firing billions of times. They're consuming massive amounts of energy and producing toxic metabolic byproducts. Specifically, they produce oxidized lipids.
Which are what? Fats?
Yes, fats that have degraded and become toxic. And if these lipids build up, they literally poison the neurons. So what researchers discovered is that during specific phases of deep sleep, the walled city does something extraordinary. It slightly lowers its defenses.
Wait, it drops the blood-brain barrier.
Just enough. It relaxes just enough to let peripheral macrophages cross the moat.
Macrophages, those are immune cells from the general body, right?
Yes. Macrophage literally translates to big eater. They're the sanitation trucks of the immune system. So during sleep, these peripheral immune cells cross into the brain, hunt down these toxic lipid droplets, and undergo phagocytosis.
Meaning they eat them.
They literally swallow the toxic fat, digest it, and haul the waste back out of the brain to be processed by the liver.
That is wild. The state sanitation department crosses into the quarantine city at night just to take out the garbage. And the study showed that if you disrupt this specific sleep phase in animal models and those sanitation trucks can't get in, the lipids accumulate, memory function plummets, and their actual biological lifespan is significantly shortened.
Which perfectly explains the visceral, physical sensation of profound sleep deprivation. When you pull an all-nighter, you don't just feel tired, you feel poisoned.
Because you literally are. The toxic lipids are accumulating.
Exactly.
And speaking of feeling poisoned, let's talk about the mechanics of a microsleep. Because there is a fascinating study out of MIT regarding attention lapses. We have all been there. You pull an all-nighter, or you have a newborn baby and get zero sleep, and you are sitting in a meeting the next day trying your absolute hardest to focus.
Oh, it's agonizing.
And suddenly you just zone out. You stare at the wall, your eyes glaze over, and you realize you haven't heard a single word spoken in the last 10 seconds. What is physically happening in the hardware of the brain in that moment?
The MIT researchers made a brilliant discovery here. They found that these uncontrollable attention lapses in sleep-deprived individuals perfectly coincide with actual waves of cerebrospinal fluid, CSF, surging through the brain.
Wait, the fluid that washes the brain during deep sleep is suddenly washing the brain while they're sitting upright in a meeting?
Yes,
How do they not just pass out on the desk?
because it's a localized forced shutdown.
Yeah.
The tired brain is so desperate for its maintenance routine that it literally cannot wait for you to go to bed. So it isolates a specific network, say the visual or auditory processing circuit, and forces it to go offline. The neurons in that specific area literally shift into a slow-wave electrical pattern identical to deep sleep, and the fluid rushes in to clean that specific localized area.
That is crazy.
Your conscious mind is trying to pay attention to the meeting, but your brain is essentially saying, if you refuse to take the whole system offline for maintenance, I'm going to shut down the auditory circuit right now to clean it myself.
That is terrifying and amazing. It's a localized brownout in the brain's power grid. And this connects directly to the NIH experiment, where researchers managed to artificially trigger sleep-like restorative effects in small parts of an awake mouse brain.
Yes. By using optogenetics, which is shining light on genetically modified neurons, they forced a small patch of the awake mouse's cortex into a slow-wave sleep pattern.
But the mouse was awake.
Fully awake, the mouse was running around doing its thing, but that one tiny piece of its brain was technically asleep. And doing that entirely reversed the memory deficits caused by sleep deprivation. It proves that the benefits of sleep aren't just about global unconsciousness. It is about the local mechanical recalibration of overtaxed synapses.
So sleep is deeply mechanical. But sleep isn't just a janitor sweeping up lipids. It's also like the librarian organizing all the data. I want to look at the mechanics of REM sleep and neural differentiation.
Right. Neural differentiation is a massive computational problem the brain has to solve every single night. Think about your daily life. You have highly repetitive experiences. Let's say you park your car in the exact same parking garage at work every single day, just in slightly different spots.
Okay, sure.
The visual inputs are almost identical. The concrete pillars look the same, the lighting is the same. Why don't you constantly confuse where you parked today with where you parked last Thursday?
Well, I mean, sometimes I definitely do.
We all do.
But most of the time, I can distinguish them.
Right. And the reason you can distinguish them is because of what happens during REM sleep. That's the phase where our brains are highly active and we experience vivid dreams. During REM, the hippocampus replays the memories of the day.
So it watches the tape back.
But it doesn't just play them back passively like a movie.
Yeah.
It actively forces the neural networks representing similar experiences to separate. It strengthens the unique differences between Tuesday's parking spot and Thursday's parking spot. It is physically rewiring the synapses so that the two memories don't blur into a single chaotic concept of parking garage.
Wow. And while it's doing that, it has to solve another massive problem, which the NIMH study on systems memory consolidation brings up, the overwriting problem.
Yes, a huge challenge.
Because if I learn a completely new skill today, my brain has to form new synaptic connections. But the brain is a crowded place. How does it physically wire a new memory into the cortex without accidentally unplugging or overwriting the old memories stored right next to it?
It's a delicate operation.
It's like trying to install a new piece of software on a hard drive without accidentally corrupting the entire operating system.
Exactly. And the brain solves this through continuous reactivation. The NIMH researchers found that newly formed memories aren't just filed away once and forgotten. They are continuously reactivated and replayed during sleep for several days, sometimes weeks, after the initial learning event.
Oh, so it keeps practicing while I sleep.
Right. During slow-wave sleep, the hippocampus repeatedly sends the new memory packet up to the cortex. The cortex carefully integrates it, physically growing new synaptic spines. And then it tests the new connection against the surrounding older memories to ensure the whole network remains stable.
That is fascinating.
It is a highly delicate, iterative process of physically weaving new threads into an existing tapestry without unraveling the whole thing.
Okay, so if sleep is doing all of this, if it's dropping the blood-brain barrier to let macrophages eat toxic lipids, if it's differentiating similar memories, if it's carefully weaving new synapses, what happens when we consistently get bad sleep? What is the long-term cost of that?
Well, the sources have a 2026 meta-analysis that introduces a terrifying concept, the sleep EEG brain age.
The sleep EEG brain age.
It is a profound diagnostic tool. We used to diagnose sleep issues simply by asking people how many hours they slept. But now, by looking at the microarchitecture of the brain's electrical activity during sleep, the EEG pattern, we can actually see the physical health of the brain.
Okay.
The meta-analysis found that we can calculate a brain age based purely on how you sleep.
So what does an old sleep pattern look like?
It lacks complexity. A healthy, resilient brain produces a symphony of electrical activity during sleep. Deep, slow waves, fast ripples, and specifically, sleep spindles.
Sleep spindles, what are those?
Sleep spindles are these sudden, intense bursts of electrical activity that occur during non-REM sleep. They are physically necessary for transferring memories from short-term storage in the hippocampus to long-term storage in the cortex.
So they are like the data transfer cables.
Yes. And an older-looking sleep EEG has flattened rhythms and severely weakened sleep spindles. And the studies show that having an older sleep EEG is strongly, causally associated with a high risk of developing clinical dementia years in the future.
So sleep is basically a crystal ball. It's a diagnostic readout of the underlying hardware.
Absolutely. The sensitivity of this readout is staggering. There was a paper showing that researchers could use an AI transformer model to analyze a single night of a person's sleep data from a basic wearable sensor. And from just that one night, they could accurately predict whether that person was taking SSRI antidepressant medications.
Wait, really? Just from a sleep tracker?
Yes. The chemical state of your neurotransmitters alters the microrhythms of your sleep so precisely that an AI can essentially see the medication in your brainwaves.
That is wild. But I want to clarify something. When we talk about poor sleep, the obvious assumption is that people aren't sleeping enough. But the sleep chart of biological aging clocks from the LMLTI consortium reveals a U-shaped curve.
Yes, the U-curve of biological aging. It measured biological markers across the brain, the blood plasma, the metabolomic system, and what they found is that sleeping less than 6 hours consistently accelerates biological aging, which we expect. The clearance systems don't have time to run. But too much sleep, consistently requiring 9, 10, or 11 hours of sleep every night, also strongly correlates with accelerated biological aging and cognitive decline.
Why? I would think more sleep equals more cleaning. I mean, wouldn't extra time for the macrophages be a good thing?
It's an issue of causality. If your brain is suddenly requiring 10 hours of sleep just to reach a baseline level of function, it is usually a desperate physiological response to an underlying crisis.
Oh, I see.
It means neuroinflammation is already present, the microvessels might be damaged, the clearance systems are failing, and the brain is frantically trying to stay in the repair state longer just to tread water against the accumulating damage.
Oh, wow.
Oversleeping isn't the cause of the decline, it is the blaring fire alarm that the decline is already happening.
Okay, so let me pause here and pull these threads together. We've seen how delicate the biological hardware is. Poor sleep over decades means toxic lipids are left behind. It means synapses fray. It means the brain physically ages faster than the chronological clock. And this forces us to confront a heavy reality. Cognitive decline, or dementia, is not a switch that randomly flips when you blow out the candles on your 80th birthday. It is a lifelong accumulation of microscopic damage. So how do we stop the damage? How do we actively build a resilient architecture?
This is where the science gets incredibly optimistic. Because there is a massive paradigm shift declared by the National Institute of Neurological Disorders and Stroke, the NINDs.
Okay, what are they saying?
They explicitly state in 2026, dementia is not a normal, inevitable part of human aging.
It is a disease process, and disease processes can be interrupted.
Exactly. And the blueprint for that interruption is the 2024 Lancet Commission Update on Dementia Prevention. They compiled decades of data and identified 14 modifiable lifestyle factors.
14 factors, okay.
And the math is staggering. If we, as a society, effectively targeted just these 14 factors, we could prevent or significantly delay up to 45% of all global dementia cases.
Nearly half.
Nearly half of the suffering wiped out.
We need to spend serious time on this, because when people hear prevent dementia, they usually think of doing a Sudoku puzzle on a Sunday morning or like eating a handful of blueberries.
Right, the brain games myth.
Yeah. But when you look at the 14 factors on this list, it has very little to do with brain games. It is about whole body infrastructure. For example, the two newest factors added to the list: untreated vision loss and high LDL cholesterol.
Let's break down the mechanics of vision loss first, because intuitively it doesn't make sense. Your eyes are not your brain. Why does needing glasses predict cognitive decline?
Right. My grandfather lost his hearing in his 70s, and his cognitive decline accelerated rapidly right after. What is the physical mechanism there?
It happens through two distinct pathways. The first is cognitive load. Your brain is a processor with a finite amount of energy. When your vision or hearing degrades, the sensory data coming into the brain becomes fuzzy.
It's like trying to listen to a radio station covered in static.
Exactly. Your auditory cortex has to work incredibly hard, borrowing energy from the prefrontal cortex just to decode the static into words.
Hmm.
Because all your processing power is tied up in simply hearing the sentence, you have no cognitive bandwidth left to actually remember the sentence.
Oh, wow.
Over time, this chronic cognitive strain exhausts the neural networks.
And second pathway.
The physical atrophy caused by sensory deprivation, the brain is the ultimate use-it-or-lose-it organ. When you cannot hear well in a crowded restaurant, or you cannot see well enough to drive at night or read facial expressions, what do?
You stay home, you withdraw.
Right. You stop engaging in complex, unpredictable social interactions.
And social interaction is incredibly computationally demanding. You are reading micro-expressions, predicting responses, regulating your tone.
Exactly. It's an intense neurological workout. When you withdraw due to vision or hearing loss, you starve the brain of that rich, complex data feed. And when the neurons in the social and memory centers stop receiving complex input, they literally prune themselves.
You just shrink.
They shrink. The tissue atrophies. Fixing a cataract or getting a hearing aid isn't just about sensory convenience. It is literally plugging the data feed back into the brain to keep the tissue alive.
That completely reframes how I think about sensory health. Now let's talk about the vascular side. High LDL cholesterol, high blood pressure, and diabetes are all on the 14-point list.
This comes down to the neurovascular highways. The human brain is incredibly greedy.
Yeah.
It makes up only about 2% of your total body weight, but it demands 20% of your heart's blood flow and 20% of your oxygen. To deliver that oxygen, the brain is packed with 400 miles of microscopic blood vessels called capillaries.
400 miles inside your head.
Yes. They are so thin that red blood cells literally have to line up single file to pass through them.
So what does high LDL cholesterol do to those microvessels?
It physically destroys them. High levels of LDL cholesterol penetrate the delicate endothelial lining of these tiny vessels, creating microscopic plaques.
Yeah.
And then high blood pressure acts like a pressure washer, violently blasting against these stiffened, plaque-filled vessel walls. Over decades, this constant mechanical stress causes the microvessels to become leaky, or they simply collapse and die.
And when the capillary collapses, the neurons it was feeding just suffocate.
Exactly. It's called vascular microischemia. Millions of tiny silent strokes occurring over decades. The neurons are choked off from their oxygen supply, and they die. You don't feel it happening, but over 20 years, the density of your brain tissue is slowly being hollowed out.
Which is terrifying. Controlling cholesterol and blood pressure is fundamentally about protecting the plumbing that keeps the neurons breathing.
Spot on.
Okay, so logically, the biological mechanisms make perfect sense. But proving this works in the real world is notoriously difficult. Epidemiology can only tell us about correlations. Is there actual clinical proof that changing these lifestyle factors in older adults can physically alter the trajectory of their cognitive decline?
Yes, and this is why the 2025 U.S. Pointer trial is so monumental. It is arguably the most important clinical trial in modern lifestyle medicine.
Really? Why is that?
For a long time, researchers struggled to prove lifestyle interventions worked because they were testing isolated variables in a lab. They would give a group of seniors a treadmill program and nothing else, and the results would be marginal. But the U.S. Pointer study recognized that human biology is an interconnected system.
So it was a multi-domain intervention.
Exactly. They took older adults who were at a high risk for cognitive decline, and they aggressively targeted multiple domains simultaneously.
Like what?
They instituted rigorous aerobic exercise, transitioned them to a heart-healthy Mediterranean-style diet, pushed intense cognitive challenges, and required active social engagement.
And the crucial part here is that they didn't do this in a metabolic ward where every meal was cooked for them. They deployed this in the messy, real world of community-dwelling adults. They had to fight the friction of changing 60-year-old habits. Did it actually work?
It worked beautifully. The adults who strictly adhered to the multi-domain intervention showed significant improvements in global cognition, executive function, and memory compared to the control group.
Wow.
It proved that cognitive resilience isn't just a genetic lottery. It is a structural construct you can actively build, even late in life.
That is so empowering. I want to zoom in on the cognitive challenges aspect of that trial, though, because there is a lot of snake oil out there regarding brain training apps. Playing a memory matching game on your phone while you sit on the toilet doesn't magically make you immune to Alzheimer's, right?
No, it doesn't. Most commercial brain games only make you better at the specific game you are playing. The skill doesn't transfer to real-world cognitive resilience.
Yeah, that makes sense.
However, The sources highlight a very specific type of cognitive training that does work, backed by a 2026 NIH-funded trial, adaptive speed of processing training.
What makes it different from a normal memory game?
It doesn't train memory at all. It trains neural efficiency. It often uses something called the UFOV test, the useful field of view.
Okay, how does it work?
You sit at a screen, and an object flashes in the center of your vision for a fraction of a second, while another object flashes somewhere in your peripheral vision amidst a field of distracting visual noise. You have to identify both.
Sounds hard.
It is. And as you get better, the software adapts. It flashes the images faster, and the visual distractions become denser.
So it's forcing your brain's visual processing speed to basically accelerate.
Precisely. You are upgrading the processor speed of the brain. And the longitudinal results of this specific training are staggering. Older adults who underwent just 10 to 14 sessions of this specific adaptive training showed a significantly lower incidence of clinical dementia over a 20-year follow-up period.
Wait, really? Just a few weeks of playing a highly specific visual processing game provided a measurable shield against dementia 2 decades later. How is that physically possible?
Because of cognitive reserve. The training forces the brain to build highly efficient, dense neural networks. It's like building a massive 8-lane highway for information instead of a 2-lane dirt road.
Oh, I see.
Decades later, when the physical plaques and tangles of Alzheimer's begin to accumulate and destroy parts of the highway, the person who did the training has so many alternate routes and backup lanes that they don't show the clinical symptoms of memory loss.
So the pathology is there, but their upgraded processor can route around the damage.
Exactly.
That is the definition of resilience. Now, if we look at the physical activity domain, the nuance continues. We always hear, do cardio for brain health. But a massive 2026 UK Biobank study looked at hundreds of thousands of people and linked simple hand grip strength and pulmonary function to a heavily reduced risk of dementia. Why hand grip strength? Is having strong hands magically protecting your hippocampus?
Hand grip strength is one of the most accurate proxies for overall muscular and systemic health. And the scientific understanding of muscle has radically changed recently. Muscle is not just a mechanical pulley system attached to your bones. Muscle tissue is the largest endocrine organ in the human body.
Endocrine, meaning it secretes hormones.
Exactly. When you contract your muscles under load like lifting weights or engaging in vigorous resistance training, the muscle fibers secrete specialized proteins called myokines directly into the bloodstream.
Okay.
Some researchers colloquially refer to them as hope molecules. These myokines cross the blood-brain barrier, reduce neuroinflammation, and literally stimulate the release of BDNFs, brain-derived neurotrophic factor.
Oh, BDNF. That's basically miracle grow for the brain, right? It forces the brain to grow new synapses.
Yes. So physical strength isn't just about moving blood. It is about turning your muscles into a pharmacy that constantly injects neuroprotective chemicals directly into your brain.
That is incredible. And the flip side of physical activity is sedentary behavior, which we all know is bad. But I found a fascinating distinction in a Swedish study of 20,000 adults. They tracked sedentary behavior over years and found that not all sitting is created equal.
Right.
They separated it into mentally passive sitting and mentally active sitting.
This is a crucial distinction. Mentally passive sitting is watching television for 4 hours straight. You're physically motionless, and your brain is in a low-power, highly receptive state. The study found that this specific behavior is heavily associated with a drastically higher risk of developing dementia.
But mentally active sitting is different. This would be sitting in a chair for 4 hours while reading a complex book, doing a challenging puzzle, or using a computer to write code or solve a problem.
Right. And the Swedish study found that mentally active sitting is actually protective against dementia.
Really? Even though you're sitting still?
Yes. Because the physical mechanism here is the hemodynamic response. Even though your body is completely still, your brain is working furiously. Because the cognitive effort is so high, the brain commands the cardiovascular system to dilate the blood vessels in the head, rushing oxygen and glucose to the active tissue.
Wow.
This intense, localized blood flow physically protects the vascular health of the brain. So if you're going to be sedentary for long stretches, your brain must be actively engaged to survive it.
Which perfectly sets up our final segment. Because all of this prevention, all of this resilience, whether it's building cognitive reserve or pumping myokines into the blood, relies on one fundamental biological truth that we used to have entirely wrong.
The myth of the finished brain.
Yes. Growing up, I was always taught that the brain stops developing at age 25. Once the prefrontal cortex fully myelinates and closes up shop, you are a finished product.
Right.
And from there on out, aging is just a slow, depressing downhill slide of losing brain cells every day until you die.
It is a pervasive, deeply depressing, and unequivocally false biological narrative. The 2026 research confirms that adult human hippocampal neurogenesis, the physical birth of brand new neurons in the memory center of the brain, continues relentlessly throughout your entire life.
So even at 80 years old, if I'm doing the right things, my hippocampus is still churning out fresh, blank slate neurons.
Yes, your brain is never finished. But it's not just about giving birth to new cells. It's also about the hidden potential locked inside the billions of cells you already have. Which brings us to the stunning MIT discovery of silent synapses. This blew my mind.
Yeah, let's unpack that. It's like discovering millions of hidden secret doors inside your own house.
Exactly.
Break that down for me. What exactly is a silent synapse?
To understand it, picture a normal synapse. It's the microscopic gap between two neurons where chemicals cross to pass a signal. When you learn something new, neurons literally reach out physical branches called dendrites to form these connections.
Okay.
The MIT neuroscientists discovered that the adult brain is absolutely packed with millions of tiny, immature structures called filopodia. They are hair-like protrusions extending from the neurons. They have physically formed the connection bridge to their neighbor, but they are completely silent.
Silent meaning what?
They pass no electrical signals. They are kept in a state of arrested development.
Why would the brain expend the massive metabolic energy required to physically build millions of connection bridges, only to leave the power turned off? That doesn't make sense to me.
It makes perfect sense when you view the brain as a highly efficient survival machine. Maintaining an active, firing synapse costs a lot of energy.
Okay, true.
But the brain also needs to be ready to learn things instantly to survive. So these silent synapses represent a vast, hidden reserve of plasticity. If you suddenly find yourself in a totally alien environment, or you need to learn a complex new skill to survive, the brain doesn't have time to slowly grow a new connection from scratch. That process can take days.
Oh, I see.
Instead, it just flips the chemical switch on a silent synapse. It recruits the pre-built architecture on demand. It means the adult human brain is immensely, profoundly flexible, just waiting to be activated.
And nobody proves that flexibility and resilience better than the superagers.
Superagers are the ultimate biological counterargument to the idea that cognitive decline is inevitable.
Who are they, exactly?
These are unique individuals over the age of 80 who possess the episodic memory function and cognitive recall of typical, healthy 50-year-olds.
We have incredibly detailed sources from Northwestern University and the University of Illinois, Chicago, detailing the biology of these individuals in 2026. And the crucial takeaway is that the difference isn't just behavioral. It's not just that they do more crossword puzzles or have better attitudes about aging. Their brains are fundamentally physically different.
Yes, they possess a unique, resilient signature at the cellular level. If you look at a typical brain suffering from Alzheimer's disease, the pathology sharply stalls neurogenesis. The toxic environment kills off the stem cell's ability to make new neurons.
Right.
But when researchers examined the brains of superagers, they found their hippocampal regions were wildly aggressively active. The Northwestern study confirmed that superagers' brains produce at least twice as many new neurons as their typical healthy peers at the exact same age.
They are just outpacing the damage. Their brains are in a state of constant, aggressive structural renewal. So the obvious question becomes, if superagers can naturally renew their brains, can we artificially flip those switches in people who are already declining? Can we actually reverse the damage?
We are getting incredibly close. Scientists are finding ways to directly manipulate the metabolic engines of the brain cells. There's a fascinating 2026 study about a survival switch linked to sugar metabolism.
Okay, how does that work?
Well, brain cells run primarily on glucose. Researchers found that by artificially altering how a sick brain cell processes that sugar, essentially starving it of its normal metabolic pathway, the cell panics.
It thinks it's dying.
Exactly. And in that panic, it flips a genetic survival switch. It forces its mitochondria to become hyper-efficient. And that triggers a massive internal cleanup operation that clears out toxic proteins and actually slows down the neurodegeneration process.
So just by tweaking the fuel source, you force the cell to repair itself. And there is another study here where they reversed memory loss in mice by targeting the mitochondria directly.
The mitochondria, the powerhouses of the cell. What that study proved is that a significant portion of what we diagnose as cognitive decline or memory loss isn't actually the structural death of the brain cell.
It's an energy failure.
Exactly. The neuron is still there, the synaptic connections are still physically intact, but the cell is so metabolically exhausted that it simply doesn't have the electrical juice required to fire the signal.
Wow.
When the researchers temporarily boosted the mitochondrial activity with a targeted drug, restoring the cellular energy grid, the mice instantly regained their memory function. The hardware wasn't broken, it was just unplugged.
That is incredibly hopeful. But I want to close this segment on a slightly darker note because it circles back to the very first thing I said in this deep dive, the self-erasing brain.
Right.
For decades, the dominant theory of Alzheimer's was the amyloid cascade hypothesis. The idea was that this toxic protein, amyloid beta, built up like plaque on your teeth and just passively smothered and crushed the brain cells to death. But the 2026 research reveals a much more insidious, active demolition process.
It is deeply unnerving. The researchers discovered that it isn't just the passive accumulation of plaque. The amyloid beta, combined with chronic neuroinflammation, converges on a specific molecular receptor on the surface of the neuron.
Okay.
When this receptor is triggered by the toxic environment, it causes the neuron to fundamentally panic. The neuron begins to release chemical signals that summon microglia, the brain's immune cells. But instead of cleaning up the plaque, the microglia are tricked into attacking the neuron's own synapses.
The disease literally tricks the brain's immune system into eating its own memories. It is an active, suicidal pruning process.
Yes, the neuron actively dismantles its own communication bridges. But the scientific silver lining here is massive.
Which is?
If synaptic loss is an active biological process driven by a highly specific receptor, it means it is a druggable target. If pharmacologists can design a molecule to block that specific receptor, they can stop the microglia from eating the synapses. They can freeze the deletion process in its tracks.
It shifts our entire view of the brain. It is not a passive victim of aging, slowly decaying like an old piece of fruit. It is an active, highly regulated machine. And if we understand the machinery, we can repair it, protect it, and optimize it.
Exactly.
So let's do the grand synthesis of everything we have covered today. We started this deep dive looking at the fortress of human cognitive autonomy. We examined the incredible mechanical reality of modern neurotechnology. Yeah. We saw how AI-powered BCIs are drilling into the cortex to restore the voices and the physical autonomy of those locked inside their own bodies, bypassing broken spinal cords, predicting their inner speech, and letting them walk with robotic limbs that can actually feel the ground.
And we explored the violent, metabolically intense cleaning process of sleep. We saw how the blood-brain barrier drops its defenses just enough to let immune sanitation trucks haul away the toxic lipids of the day. We saw how the brain forcibly shuts itself down in microsleeps just to survive, and how the microarchitecture of your sleep waves predicts the physical future of your mind.
And we demolished the myth of the finished brain. Armed with the 14 pillars of prevention, the activation of millions of silent synapses, and the cellular secrets of the superagers, we understand that cognitive decline is absolutely not a foregone conclusion. We are the architects of our own cognitive resilience.
Beautifully said. But before we go, I want to leave you with one final, deeply provocative concept from the sources.
Let's hear it.
We have spent this entire deep dive talking about conscious effort. The effort of exercising, the effort of learning, the effort of controlling a BCI, the effort of organizing memories. But a 2026 Nature study looked at patients under deep surgical anesthesia.
Oh, okay.
Their conscious minds were completely chemically forced offline. They were entirely unresponsive to the physical world.
Completely shut down.
So we thought.
Oh.
But high-resolution brain recordings show that even in that profoundly unconscious state, their auditory cortex and memory centers continue to process complex patterns in the words and sounds happening in the operating room.
Wait, really? While they were under the knife?
Yes. They weren't just passively hearing noise. The brain networks were actively learning the statistical probabilities of the sounds, predicting what came next, and physically reacting to surprises in the audio pattern. The biological machine was still relentlessly learning without a single shred of conscious awareness.
Which brings us right back to the ultimate question of autonomy. If your brain is constantly processing, constantly learning, and physically rewiring its own microscopic architecture even when you are entirely unconscious, even when you think the systems are shut down, what invisible habits, what background noises, what passive environmental exposures are quietly shaping your brain's architecture right this very second? Your mind is a relentless, ever-adapting machine learner. It is always listening, and it is always building. Make sure you are feeding it the right data, keep exploring, keep protecting the fortress, and we will see you on the next deep dive.